There we go. Okay, you can see my slides, you can hear me, hopefully. I can kind of see you because there's light shining in my eyes. Before I start, I've got a little bit of housekeeping. So my colleague Emily gave the closing keynote yesterday, and she mentioned that ThoughtWorks is hiring data roles across Europe, multiple cities, multiple countries. So if you are still interested in that and you didn't get a chance to scan the QR code, now is your chance if you want to work with some lovely, clever people. Now, the other thing I have to say before I get started with this talk is there is a content warning on this talk. This talk is about AI ethics. So we are going to be looking at some examples of building AI systems that have gone wrong, have had negative impacts. So we are going to be looking at examples of discrimination, of racism, and also transphobia. We're not going to be going into great detail on these failures, but we will be covering them in a couple of slides as examples. So full warning there. And one final content warning is that there's also going to be one kind of weird picture of the inside of a fish. So if you have a, easily turned stomach, heads up there. So this talk is about how to build AI systems ethically. And I am not going to give you a silver bullet. I'm not going to give you a magic solution that is going to solve all of your ethical problems. In fact, a lot of this talk is about how there aren't any silver bullets in this space. But I also, at the same point, do want to give you something you can take away, something you can apply to approach building AI systems and really any software systems in ethical ways. So that's the talk, right? It's about AI ethics. Let's start with the obvious question. What are fish? So for reasons I legally can't get into, I had to answer this question recently. And I did the obvious thing. I started on the internet. I went to a popular search engine and I searched for what are fish? And one of the first results I got was from the New Mexico Department of Game and Fish. Now, this is an entire department devoted to fish. So you think they'd be quite good at this. And the description they gave, the definition they gave was that fish are cold-blooded vertebrates that live in water. Nice and simple. Maybe this is very similar to the definition you heard when you were at school. I like it. Simple, understandable, but there is a problem here. The problem is this phrase, cold-blooded. Because most fish are cold-blooded. But this is the OPA. And I don't know about you, but that looks like a fish, and it's warm-blooded. So yes, most fish are cold-blooded, but not all of them. So that cold-blooded can't really be part of the definition of a fish. So I had to go back and search again. I had to find a better definition. On A2ZAnimals.com, fantastic source for all your animal-related facts, they said that fish are aquatic vertebrates. Nice and simple. They live in the water. They have a backbone. Easy. Did a little bit more searching. I found that National Geographic, another excellent source, says basically the same thing. Fish live in water and have a backbone. Again, exactly the same definition, right? So I'm feeling quite positive about this. We've got multiple sources agreeing on the same definition. It's nice, simple, it's high level, it's easily understandable. Good. Now, fish live in water and have a backbone. Unfortunately, this definition does technically include this guy. But that isn't the real problem here. The problem here is the hagfish. The hagfish is a sort of eel-like creature, very slimy, lives underwater, and you can tell from its name, it's a fish, and it does not have a backbone. If you cut it open, you'll see it's got this sort of slimy column on the inside, but no bones in there. So that definition of fish being vertebrates that live in the water excludes the hagfish. So there's a problem there. So I went back and I searched again. And I found this definition from Arts and Culture at google.com that says that fish are aquatic craniate animals. Now, craniate just means they have a cranium, they have a skull. It doesn't say anything about the backbone, just the skull, okay? This is a better definition because our friend the hagfish, back in the game. They're a fish again. Good. I am feeling very good about this definition. I think we've solved everything. But unfortunately, there is a question we have forgotten to ask right now. We have forgotten to ask, what about whales? Now, whales, as you can see, live in the water. They have craniums, they have skulls, very big ones, in fact. But they don't breathe underwater. They have to come up to the surface to breathe. That's interesting because most fish that we think of have gills. These semi-permeable membranes that allow water and air into their body. And that poses a little bit of a problem. How do we deal with this, right? Whales.org takes a very hard line against this. They have an entire page on this about how whales are not fish. You might have learned this in school as well. Whales are not fish, they're mammals, they just happen to live in the water, right? So we're going to need a better definition. I went to the big guns now, I went to Wikipedia. And they said that fish are aquatic, craniate, gill-bearing animals. All right, now we're starting to get a more complete view here. Looks pretty good, but there is another problem, and that problem is evolution. You might remember that life evolved in the oceans. I mean, you probably don't personally remember that, but you might remember learning it in school. And at some point, those fish crawled out of the ocean, they came onto the land, and they became something else. They evolved into, all of us and all those other lovely things. So where do we draw the line here? When do they stop being fish and start being something else? Well, we could say that as soon as they start using their fins like legs, like limbs, they stop being fish. That would be nice and simple. But that then poses a problem for the roughback batfish. Now, I think we need to talk about the roughback batfish because I get the roughback part, okay? It's very clearly got a rough back, okay? I do not really see the resemblance to a bat, personally, but okay. But you'll notice the roughback batfish is actually standing on its fins. It's using them like legs, and yet it still swims around. It's still a fish, which again, you can tell from the fact that it has fish in its name. So how do we deal with this? Again, we can look to evolution here. One of the first animals that came out of the ocean was the Tiktaalik. And one of its distant relatives, about 10 million years later, is the Acanthostega. This is after about 10 million years of evolution. Something's changed. Can anyone see the difference here between the Tiktaalik and the Acanthostega? The difference is in its hands. The difference is in its fins. You see, the Acanthostega has fingers. So this is what we're going to use. See, as they evolved, as it spent more time on land, it started evolving digits. Fingers, essentially. So that is the definition we are going to use. The full definition from Wikipedia is that fish are aquatic, craniate, gill-bearing animals that lack limbs with digits, okay? Finally, our friend the roughback batfish is back, and we are good. We have solved it. This is our definition of fish. So we're currently about 5 minutes into a talk on AI ethics, and I have spent, the first 5 minutes talking about fish. Why am I doing this? See, I do this because whenever we define something, whenever we define rules about what is and isn't a fish, we draw a line. We draw a line between what gets included in this set and what gets excluded. And there isn't one perfect answer here. If I'm explaining what a fish is to a 4-year-old, I might just say fish are animals that live in the water. That's good enough. That's fine. If I'm explaining it to a 9-year-old, a 10-year-old, I might explain that fish are cold-blooded animals that live in the sea. And I know that's wrong. I know that doesn't quite capture the full complexity of fish, but it might help the kid understand the difference between warm and cold-blooded animals. If I'm running a fish farm that farms octopus, even though they wouldn't count as fish, I might include them in that definition there anyway. See, there isn't one correct way to draw this line. There is not one single, consistent, perfect, correct definition of fish, but we need to make a decision about where we draw that line for a given context, for a given problem. And when we do that, we make a choice to include some and exclude others. And this process of line drawing, this process of defining rules that include and exclude, is something we do a lot. We do it when we have acceptance criteria. Here are some acceptance criteria for a password, right? We are going to accept the password if it has more than 10 characters. We will exclude the password if it has less than 10 characters. We're defining a rule between acceptable and not acceptable. This is a job advert. It did the rounds on social media a little while ago, and it's got all the normal things you would expect in a job advert, right? So at the top, we've got the job details, the salary, the job type, the location. And some of you might have read a little bit further down, and you've noticed there's a little note here, that says, only born US citizens, brackets white, brackets don't share with the candidates. Now, they've made two very important mistakes here. First, they were incredibly racist. Second, they did share with the candidates. They have defined a rule here about who gets included in the set of people who they are allowing to apply for this job, who is considered for the job and who is not. They're making an ethical choice about who to include and who to exclude. Sometimes it's very obvious where this line is being drawn, and sometimes it isn't quite so obvious. Sometimes people hide behind questions, like when fascists ask the question, what is a woman? I'm not just throwing around the word fascist here. The person who directed this movie identifies as a fascist. And when he asks this question, he's not exploring the complexity of human experience. He's trying to draw a line in a very specific way that excludes the people he wants to exclude, that discriminates against the people he wants to discriminate against, and includes the people he does want to include. So hopefully you get my point here. When we define rules, we're making an ethical choice. We are deciding who gets included and who gets excluded. This is relevant because we do this all the time. So now we need to talk about AI. And once again, we should start with the obvious question. What is AI? As with fish, there is not one perfect answer to this. There is not one simple, correct answer that will be perfect in every case. But we do need to define it for the purposes of this conversation. Otherwise, we're just talking about nothing. And the definition I want to use is I want to compare two types of systems. The first is what we could call a rule-based system. This is the kind of traditional computer code you've written, almost certainly have written. If the password length is less than 10, we reject it. We throw up an alert. This is quite literally a rule. An if statement is a rule. This is an algorithm. This is, again, what we would think of as traditional computer code. And I want to compare this with what we might call a connectionist system. Connectionist systems are built of networks. Networks of nodes, of neurons with weights and embeddings in these systems. This is a very different type of system. Neural networks are these systems. Large language models are these systems. And the reason I want to kind of call these out as AI is because a lot of what, and this is, sometimes articulated as a big pile of linear algebra. But the point is, it's a very different type, a very different approach to building systems than these traditional rule-based systems, what we might also call symbolic systems. The reason I want to kind of call out connectionist systems and why I want to focus on these as AI systems is because neural nets comes under this category. Neural networks are quite literally connectionist systems. Large language models are connectionist systems. Machine learning, deep learning, support vector machines, all of these are connectionist systems. Anything built by OpenAI is a connectionist system. ChatGPT, DALL-E, Midjourney, GitHub Copilot, all of these systems are connectionist systems. The reason I want to focus on these is because this is where people are focusing right now. I think they are, in a very meaningful sense, a step change from traditional systems, traditional computing, but also this is where a lot of money and effort and interest is right now. It's not a perfect distinction. Some people would and have built what we would call AI systems using rule-based systems. These are also known as symbolic systems. Some people have built what's known as good old-fashioned AI using these rule-based systems. But I really want to focus on these connectionist systems today, because when we talk about AI, 90% of the time, that's what we're talking about. So now it's time to talk about AI and ethics. Let's pull these two things together. I said a few slides ago that whenever we define rules, we make an ethical choice. Not every rule we define has a huge ethical impact. Excluding passwords less than 10 characters probably doesn't have a huge ethical impact. But when we define those rules, we do make an ethical choice about who to include and who to exclude. So when we're looking at these two types of systems, we can ask a very simple question. Where are the rules? Well, with the rule-based systems, they're right there. It's in the title, okay? An if statement is quite literally a rule. If it is less than 10, we do this. If it's more than 10, we do a different thing. That's the rule. But where are the rules in the connectionist systems? Because when we define those rules, we are taking on an ethical responsibility. Where are they? These connectionist systems apply rules. This is an image recognition system that is classifying things as cars or bicycles or traffic lights or trucks. There is a rule here about what a car looks like, what a bicycle looks like. Even generative AI. When we ask DALL-E to produce this monstrous pictures of top engineers, it only shows white men. There is a rule there about who is included in this representation and who is excluded in this representation. There is a rule. Even when we look at the effectiveness of our different AI models, we sometimes visualize them like this. On the left, we have our input data, some red dots that we want to classify as red and some blue dots we want to classify as blue. And then we visualize how well our different approaches work, what percentage they get correct. And again, you see these lines. Where are things classified as red and where are things classified as blue? We are drawing these lines, we are defining these rules, but where? So we see the rules being expressed. They are applying rules, they're having an ethical impact on the world, but where are those rules being defined? It's somewhere in this big pile of linear algebra. But it's not in any one of these neurons. That's the interesting thing about connectionist systems. You can't open up one of these neurons, one of these nodes in the network, and find the rules. There isn't an if statement hidden in here that defines what a car looks like. The rules are in the connections between the nodes. They are distributed throughout the network as a whole. With connectionist systems, we have what's known as distributed rule representation, which means it's very difficult to understand what those rules really mean, where they are really defined. And this is where explainable AI comes in. The whole point of explainable AI as a field is to make this big pile of linear algebra, to make these connectionist systems more understandable, more explainable. We know when we're building these systems, they're having an ethical impact on the world. They are expressing our ethical intent. So we want to make sure we can understand them and grapple with those topics as effectively as possible. Here's a great demo. It's a really interesting demo. This is from an IBM research lab. It shows a couple of people who've been denied a loan by an AI system. And this framework explains why. So it says, Jason's application has been denied, and there are multiple factors contributing to it. The value of consolidated risk markers is 65. It needs to be around 72 for the application to be approved. Does this for a couple of factors. Even talks about the relative weighting, the relative importance of these factors. Some of these are more important than the others. This isn't always useful. If I'm building a system to identify cancer, for example, it probably matters more that I'm accurate than that the system is able to explain why. But there are times when this genuinely has utility. If Jason's loan application gets denied, giving Jason some information that he can use to understand why, to engage with this and take some steps to improve his chances next time, that can be really useful, just simply from a user experience perspective. If there's a human in the loop, Jason can call them up and say, hey, I think you got something wrong. They can look at this explanation and decide whether or not it's appropriate for them to override it. This has some utility, but there's something really interesting about this visualization, about this demo. I don't know if you've noticed it. Look at the wording on this page. It says that the value of consolidated risk markers is 65. It needs to be around 72 for the application to be approved. Average age of the account is 52. It needs to be around 68. And it keeps using this language. It needs to be around 3. If you do these things, it will improve the likelihood of being accepted. At no point does this say, if you do this, your application will be approved. It makes these soft, probabilistic statements. Move in this direction. It will improve your likelihood. To understand why this is, we need to talk about complex systems. So again, let's ask the question, what is a complex system? And there's a lot of definitions out there, a lot of definitions I really like. But the definition I'm going to use is from the book Complexity and Postmodernism by Paul Cilliers. This is probably the most often widely cited definition of complex systems. In this book, Paul lays out a couple of properties that all complex systems have. He says that complex systems have a large number of elements, lots of moving parts. That's necessary, but it's not sufficient. After all, sand on a beach, lots of moving parts, but that's probably not what we're thinking of when we say complex systems. Those elements also need to interact dynamically and richly. They exchange information between each other. They interact in different ways. Some of those interactions are non-linear. So a small input can lead to a very large output. Most of those interactions are short range. Those interactions can have loops. They're open systems. Complex systems, it's very difficult to draw the boundary of a complex system. Where does it end and where do other systems begin? Because they're constantly interacting with the systems around them. They operate very far from equilibrium. They're not just evolving towards some final state. They have a history that informs their present, informs what's possible in their current behavior. And importantly, they have this property known as locality, which means that no element in the system understands the whole system. If one element in the system understood the whole system, then you could collapse the whole system into that one point, and it wouldn't really be a complex system. These complex systems are dynamic. They're co-evolving with their environment. They're unpredictable. Not truly stochastic, but it's almost impossible to make deterministic statements about their behavior. These are very difficult systems to work with. Let's look at an example, right? An obvious example would be society. Society has a lot of elements, right? Lots of people in society. Those elements, those people interact dynamically and richly. They talk to each other, they share information. A lot of those interactions are non-linear. You can start a rumor. Small input leads to very large output. Most of those interactions are short range. You can talk to people on the other side of the world, but you mostly talk to people who are nearby. Those interactions can have loops, feedback loops, rumors again. They're open systems. How do you draw the boundary of a society? Where does it end? That's an almost impossible question to answer. And they operate far from equilibrium. They're not just evolving towards some final state. Society isn't going to be done one day. They have a history. The history of our societies informs what's possible today. And they have locality. Nobody in society understands all of society. So society is a complex system. And so is AI. So are these connectionist systems. They also have large numbers of elements. They interact dynamically and richly, non-linear interactions, sigmoid activation functions. They're typically short-range interactions. There's loops in the interactions. They are open systems. They include the data that goes into them and the world that they interact with. They operate far from equilibrium. They have a history. They're informed by how they're trained. And they have locality, because you can't find all of the rules in one of the nodes. Society, the world around us, is a complex system. And so are these connectionist AI systems that we are building. So what this means is, when we use AI to model some aspect of reality, some aspect of the complex reality around us, we're using AI, we're using a complex system to model a complex system. And this is really important. As Paul Celius puts it, a complex system cannot be reduced to a simple one unless it wasn't really complex to start with. Complexity is incompressible. You cannot reduce a complex, dynamic, ever-evolving system to a simple set of rules. This has huge implications, and this is a part of the sales pitch of AI. Think about the classic example of machine learning, right? Who here has done a machine learning boot camp or a course where you trained a neural network to do character recognition? Has anyone done this? Yeah, I see a few hands going up. Because it's a trivial example. You can train a network on your laptop in an afternoon to do this. It's really not that hard, okay? For a connectionist AI system, this is trivial to do, but for a rule-based system, this is impossible. What set of angles makes this a 5? Can you write down every possible angle, every single possible version of the number 5. You could try, you might capture some elements of it, but you're never going to capture all of it. This is the sales pitch of AI. These connectionist AI systems are able to deal with complexity that traditional rule-based systems simply cannot. But there's a downside to this as well. As Paul Celius puts it, because complexity cannot be compressed, it follows that any proper model of a complex system would have to be as complex as the system itself. As a result, the behavior of the model will be as complex and unpredictable as the system itself. The more complexity we model with an AI system, the more complex that AI becomes. I think of this as the contradiction of AI. This is an unavoidable part of AI. Think about it this way. Why did the United Kingdom vote to leave the European Union? That is a complex question. There is not one answer to that question. I can't give you one answer to that question. And if you were to train an AI, a perfect AI, train it on every single atom since the beginning of the universe, and you were to ask it the same question, why did the UK vote to leave the EU, you would get the same answer. That's a complex question. There isn't one answer to that. We can't, because the more complexity we try to model, the more complex the AI becomes. That's why we have these words in here. That's why it gives these probabilistic statements. Your risk markers need to be around 72, because we can't deterministically state if your risk markers are around 72, you will be approved, because in doing that, you might change something else. There is, in many cases, a lack of maturity around explainable AI frameworks, yes. But the limitation here isn't technical maturity. The limitation is the fundamental complexity of reality. So explainability is sometimes nice to have, but there is a limit. There is a fundamental limit on how far this is going to take us. So if we're looking to explainable AI as a silver bullet, something that's going to solve our ethical problems here, we're kind of back to square one. Which leaves us with one more thing, one more lever we can pull here. What about the training data? We trained these models. Does this give us a lever, some way of making our AIs, or allowing us to operate and build our AIs more ethically? You don't have to look far to find examples of biased training data leading to bad outcomes. The Google Photos example here is particularly depressing. In 2015, if you searched on Google Photos for gorillas, it would return you pictures of people of color. Because they trained their facial recognition software on biased data that did not cover the variety, the diversity of skin tones that they should have done. Their lack of their biased data here caused negative impacts to their users, caused negative impacts to the world. The idea here is simple. We pour data into our big pile of linear algebra, into our connectionist systems. We train it on this data and we get out rules. So if we put in biased data, we're going to get out biased rules. This is a simple idea. That's why there's a huge amount of work. That's weird. Why is that? I'm seeing a different thing on my screen. Is that? I don't know why the main screen is not updating. Don't know what's going on there. Okay. Have we figured that out? Oh, there we go. Excellent. Okay. You missed like 2 slides. I didn't realize because I was looking down here and that one hadn't updated. So, yep, as I said, you put in bias, rules, data, you get rules, bias data, you get biased rules. So this is why there's been a huge amount of work being done on overcoming bias, getting more representative, more unbiased data sets, and also training approaches. There's a lot of genuinely good work being done here. You might have seen on the first day of the conference this idea of the sort of bias iceberg, the idea that there's multiple places that bias can enter a data set. We can have simple statistical and computational bias. We can have human bias in how we apply and how we define these rules. And we can have deep systemic bias embedded in that data at multiple steps in the process. The problem here is no matter how broad and expansive we try to make our data sets, or even whether we try to make synthetic data instead, there simply is no such thing as unbiased data. All of our data comes from a place known as the real world, and unfortunately, there's bias there. There genuinely is good work being done, but much like explainable AI, there is a limit here. I think there's a bigger problem, though. See, with all of these approaches of getting broader, more unbiased training data sets and testing data sets, what we're trying to do here is make this number go up, right? If we capture more cases in our training data, we might be able to get our classification, any part of our AI system to be more accurate. If we can get that to 100, that's great, that's lovely. And yes, to a degree, you probably should be trying to make this number go up. If your classifier is right 20% of the time, yeah, you probably have some problems. But I think there's a real problem if we focus too much on just making that number go up, we miss a much more fundamental question, which is, which of these are fish? Ultimately, we are classifying some of these red dots as red dots and some of these blue dots as blue dots. If we try and get that accuracy perfect, we ignore the fact which of them should be red and which of them should be blue. Which of these people should be denied a loan? Which of these people should be excluded from a loan? We're ignoring the fact that we are making an ethical choice in how we classify them, not just in how accurate our classification is once we've decided on that classification. The way I kind of personally visualize this is when we're working with rule-based systems, traditional rule-based systems, we define our rules, we write our acceptance criteria, what is going to be included, what is going to be excluded, we implement those rules, we write down the code, we deploy the system and we apply the rules. And to be clear, it's never this simple. This is a massive oversimplification. But when we're building AI systems, when we're building these connectionist systems, we've got a lot more steps in there. We define our rules, yes. We need to think about explainability. Which explainability framework and approach are we going to take? Is it even appropriate in this case? What are the limitations of it? We need to make sure we have unbiased training data. How are we going to do that? There's multiple approaches to that. We need to select an appropriate training approach. We need to deploy our model. The training approach and the model deployment both have impacts on how effectively this applies its rules. And then ultimately it applies its rules. And in both of the cases here, we are defining rules. We are defining who gets included and who gets excluded. And in both of these cases, we are applying those rules. We are having an ethical impact on the world around us. The only difference is there's a lot more stuff going on in between here. This is one of my key points here, is that we can't escape our ethical choices, but AI can hide them from us. AI can make it harder for us to grapple with these points, grapple with our responsibilities. So what is to be done here? I've said that explainable AI is not a silver bullet. Explainable AI is not going to solve us. It has fundamental limits. We are never going to find or make truly unbiased data. And there is deep complexity in the systems we're building that makes it harder to engage with our ethical responsibilities. So what is to be done? Well, we might look to the field of complexity science. This is a huge field. But unfortunately, the ethics of complexity cannot do more than generate an awareness of the fact that we are always in trouble. But I do think there's some useful things we can take out of this. Paul Silius puts forward what he calls the provisional imperative. This is a meta-ethical framework for how to approach ethical decisions in a complex context. And I want to try and apply this here to when we're building AI systems, and indeed software systems in general. The first principle, the first idea in the provisional imperative is that if we're building systems in a complex environment, we need to accept provisionality. That means we need to be willing to throw things away. We have to understand that the things we build might be wrong. No matter how we model our world, we are always going to miss things. Emily said earlier today, reality only happens once. It might not happen the same the next time. No matter how perfectly we model the world, we will get things wrong. And we're going to have to update our plans. We're going to have to change things. We need to accept that anything we build is fundamentally provisional. I don't know if the example I gave of Google Photos returning certain pictures when you search for gorillas. Does anyone here know how Google Photos solved that problem? Hands up. So very depressingly, the way they solved that was by stopping you searching for the word gorillas. And to be fair, that is probably a perfectly reasonable risk mitigation strategy, right? But it also kind of implies they weren't able to go in and update their model. They weren't able to go in, as soon as they realized that, hey, they had really screwed up and did not have a representative training data set, they were not able to go in and update it quickly. That happened in 2015, and you still can't search for gorillas in Google Photos. Just a little note there. So I say this with complete seriousness. I think that any ethical approach to building AI systems or software in general needs to include continuous delivery. It needs to include the ability to get your changes into production quickly and reliably, because you will get things wrong, you will need to change them, so you better be ready to do that. If you build something and it takes 6 months, a year to get it into production, you are not set, you are not prepared to deal with your ethical responsibilities. And look, I don't care if you build this responsiveness through a data mesh transformation. I don't care if you call it continuous delivery for machine learning or ML ops. Really doesn't matter to me. The point is, if you're building systems in an ethical way, you need to be ready to change them. You also need a sense of irony. A sense of irony means being willing to throw away things, knowing that you invest time in something and you're still going to need to throw it away. Irony means rejecting development plans that look like this. You've got an 18-month release process, but hey, you split it up into 2-week sprints, so you're agile. Good job. The problem with this is the reason you spend 6 months on requirements, the only reason anyone spends 6 months gathering requirements is to be absolutely sure you're right. To be absolutely sure that by the time you get to this release, you've built the right thing. That's not an ironic approach. That is committing to a plan. That is committing to a particular outcome. That is not an appropriate approach in a complex environment. There's a book I like, written by some of my colleagues, Edge. There's a line I really like in this book. It says, "It's not that we don't plan, we do. We just don't believe our plans will survive reality." That's an ironic outlook. That's the kind of outlook you need if you're going to act ethically and build things. You need to be willing to throw things away, be willing to accept when you're wrong and change your plan. You also need creativity. As we're exploring new things, we need to be able to really explore interesting new spaces, explore new possibilities, challenge and question the status quo. There's some great guides here. I like the Responsible Tech Playbook. It has a collection of techniques and workshops and practices to explore ethical risks and alternatives and possibilities. There's some really good stuff in here. I think you should follow approaches like this. But I think you need more than this. You really need diversity in your team. You need to include a broad swath of people in your team in the process of actually building this thing. Look, it doesn't matter what workshop format you're following. If the only people in the workshop look like me, you are going to be missing out on a lot of perspectives. And you need those different perspectives. You need genuine, broad, diverse perspectives to truly creatively explore possibilities. Diversity and inclusion is not a nice to have, it is an ethical imperative. And you also need transgression. You need to be willing to question and push back against the status quo. You need to be willing to deconstruct systems, to question them, sometimes to throw them away and sometimes to rebuild them. It doesn't mean just throwing away things for the sake of it, but it means being willing to do that when you need to. A friend and former colleague of mine, M, was talking with Martin Fowler a couple of years ago on the subject of data science. And they said something that really stuck with me. They said that the biggest question, the most pressing question in data science is, couldn't we just use a linear regression for this? I like this quote. It's a good quote, right? For all of the hype around deep learning and large language models, sometimes the thing you need is a linear regression. Sometimes a linear regression is fine. It's going to solve your problem, and it's going to be much simpler. It's going to allow you to engage with your ethical responsibilities much more effectively. Transgression means sometimes we look at the systems we're building and we say, look, this is going to be difficult. We need to really take our time, assess our risks, invest in explainability, invest in broadening and making our training data more unbiased, and really managing our risks here. Sometimes transgression means saying, what if we just did a linear regression instead? That would make it a lot easier for us to engage with our ethical responsibilities. And sometimes transgression means saying no. Sometimes transgression means saying, there is no way for us to build this in a way that is consistent with our moral values. So we are not going to build this. Transgression doesn't mean throwing things away for the sake of it, but it means being willing to do that when it's needed. So that's the provisional imperative. A sense of provisionality, a willingness to throw things away, and a sense of irony around that. Creativity, to explore new possibilities. And transgression, to push back when you need to push back. This is a meta-ethical framework. It's not meant to solve all of your problems, but I do think you need this when you approach engineering problems in a complex world. Day to day, you're going to have much more pressing concerns. There are regulations around AI. The AI Act is currently being formulated. This is likely going to be directly impacting a lot of your work day to day. There are a great many frameworks and guides and techniques to help you engage with ethical responsibilities day to day. There's some really good papers here. I will have references at the end so you can download all the papers. They're all freely available. Some of these are practical, like here's a workshop you can run to explore your risks. Here are ways you can articulate and reason about harm reduction. There's some really, really good stuff in here. This is practical day-to-day stuff that you will need to and should be using. But whatever law you're following, whatever workshop you're running, whatever technique you're using, you're still going to need this. You're still going to need to be keeping these things in mind. This is a meta-ethical framework, and I do think it's something that should be informing everything you do. Because really the whole point of this talk is that we can't escape complexity. We can't escape the complexity of the world around us. In some cases, we can't escape the complexity of the systems we're building, although that is something we have at least some control over. And we can't escape our ethical responsibilities either. When we're building systems that have an impact on people in the world, we have an ethical responsibility to them. But we can choose how we take on those responsibilities. Thanks. That's the end. You can download all the stuff, the references over there. The end.